Everyone get that? 0.1166291. Okay, so pi, if I have the function of pi equals 2 to the negative pi, put in a 2, the caret, a negative, the pi, and enter. God bless you. Should get up 0.1133147. Okay, on the function of 3/2 equals 0.6 raised to the 3/2 power, so 0.6 caret. Are you all right, Aubrey?
Yeah.
Okay. Caret, and then you've got to open up a parentheses. 3 divided by 2, close your parentheses, and push enter. So 0.4647580. Okay. Now, if you have a calculator that does not work with those particular keystrokes, you need to research that and find out how it is that you need to work that. It will make this logarithms so much easier if you're able to do that. Okay, so I'm going to try the checkpoint here. F of x equals 8 raised to the negative x if x is square root of 2. So I have 8. I'm going to raise it to square root of 2.
What'd you get on the checkpoint? We're at negative right.
I got 18 something.
18.9350009.
We're at 0.05.
See, and you've got it right. What did I do wrong?
Oh,
I put it in parentheses.
We didn't put in parentheses.
no, I put in the square root of 2.
Yeah, but you didn't put it in parentheses.
No,
Before
See?
before the square root.
Mm-hmm.
Okay.
you gotta separate the negative and
Wow.
Oh.
You're a genius.
yeah, I just put extra stuff.
Function value f of square root of 2 is equal to 8 to the negative square root of 2 power. Use the calculator keystrokes 8 caret left parenthesis negative square root 2 right parenthesis enter. You should obtain a display of about 0.0528248.
Okay,
Use the
so
calculator to evaluate f of x equals 8 to the negative x at x equals square root of 2. When x
it's good to know that we've got to use the parentheses. So that's why I definitely want to do that one.
When I go to do that online, it won't let me do that. It says if there's an error.
They won't let you do the parentheses?
No. Like I put 8 to caret, and then I put a parentheses, and then I do another one for the negative, or do I have to put the negative on the outside of that first?
No, don't do another parentheses. Just one.
I thought that that's the way they had it.
No. They have parentheses, then the negative, then the square root, then 2, then in parentheses.
Okay. I got
That is not what that was supposed to be.
How many more class sessions do we have?
About 3.
That's it?
Yeah,
So when's this class in?
whenever we're done. Actually, it'll be the first week of May. For sure, but we may be done the week before that.
Monday? That's wild.
What?
That's wild.
We only have a month left of school.
That's crazy.
What?
Yeah, it's great. I have a month till I go to Colorado and I'm going to Glenwood Springs.
There you go.
What?
Yeah.
I have
Classes start, or our finals start May 5th. And our classes.
What?
Yeah.
I have a class at Fort Hayes.
I have 2 classes left for Comp 1. I have this week and I have next week.
I don't either, but like, it's abnormal state college, there's a lot of like lecturing, and there's not a whole lot of assignments, so if you do bad on one assignment, it tanks your grade, and that's me right now, it's like, shit.
I mean, I don't have a class on Fridays for 4 days.
That's wild.
The semester was like fast.
That's freaking wild.
Especially with speech.
They can't believe they don't have
Watch
very
the
much
summer
longer.
go by, like.
It's crazy.
Get it back.
I mean, my summer went by slow. I need another summer like
I'm gonna start doing 12s this summer, so it's hoping to go by.
I don't know why
Yeah,
in the
have
summer I'm
to
getting as
assignments
many
too.
trips as I can, as much sun as I can, because I want to be as tan as I was last summer.
I'm going to Colorado, it's really trigger.
I know why.
I have Colorado and May 9th. through
I printed it
11th.
off of here.
Well, I'm going to Hawaii with my friends in Colorado, we'll be gone for like 3 to 4 days.
And
Should
then
not matter, I'm on vacation.
Yeah, it does.
Arkansas in June, Miami in July, Vegas in September.
What?
Taking this money.
See, because I was in that room to begin with, right? So I bet that computer is hooked up to your printer.
I'm just
Miami,
gonna
one
try
of my
not to
friends is
get,
actually.
It
taking
still
it.
shouldn't be though, because that was the
That's
printer, that was a
me.
business printer.
I'm just gonna try not to get alcohol poisoning. That's
Unless
my.
I just want to get as tan as I did last
Which
summer.
that could
I
be.
still
They
have
didn't
tan
move
lines
them.
from
This has been the one
I'm
that's
trying
been
to
here.
avoid tanning.
I
I
need
don't
my
like it
tan.
super dark.
I wonder if I inadvertently was
Anytime I wear anything light colored.
sending all of that
it's
stuff
super boring.
to your printer.
I have a bunch of late days this summer.
Could be.
Because when we turned that on, it had to have printed because I didn't do anything
It's gonna be a good summer.
about this.
About best friends and
That's why you look so confused.
Yeah, yeah, because see, the other day, I worked on this on Saturday. And so I'm like, what the hell? But I printed it, but my printer was off. And so I didn't walk into the office to turn it on. And so it must have,
Just printed.
when we turned it on in here, said, oh, we see a printer, so
close to that point.
That could be.
You just gotta flirt with.
I wonder if I was printing stuff and not even meaning to.
What?
I know
Does it
that
drink like a lot?
Could be.
Oh,
You know, when we were having all that
Yeah, all
printing.
those issues.
Because
I know that you don't
But if
have
that
to do
computer
it
never got
hospital
changed, then that would
all
make
the time.
sense. Why
Somebody
was
will make you throw up.
not doing the what it was supposed to
That's
do,
happens
you
all
know?
Uh-huh.
through high school.
that was me on Sunday.
That would totally make
I've never
sense.
been that drunk, I've never been completely drunk before.
What? You're missing out, sweetheart.
well, thank you. I needed this printed.
You're missing out.
Because I have to amend it and I have to send it in.
I don't,
To amend it.
I don't like drunk people, I don't like parties.
So,
I don't
my-
party before I do.
I mean, I don't
wonder what
I don't
this
do
is.
parties. I've never been to a party.
Well, you know.
think that's what
I've
Earl
never
was
been to
here.
a party.
Thank you.
Hang out.
Yeah, you're missing
What was I
out.
doing?
All right.
Oh, I met my
Notice
neighbors
I
this
did
weekend,
my-
and they had 4 cops at this apartment complex on 8th and Hall. They were partying
That's what I
right
see.
across the street, and we were playing NWA, fuck the police, as loud as we could with the garage door open. And we went to close it, because there's like 4 cops there, and they're searching this guy for drugs, so what's, they could get rid of a cop and come and bust our house party. And we're all minors. We go to close the door, and the neighbor's like, nah, we do this shit every weekend. Open the damn door. So we did. We were totally mocking them. We were playing like Bad Boys. What other songs?
That's funny, I hate that.
Harbor Freight's coming to town.
It was hilarious. And I don't like police in this town either. And I was like,
See,
yeah,
I know.
Okay.
really? They're assholes to me. I don't like them.
There's only one that I don't like, and it's because my sister
I don't.
is an ass.
But
I haven't dealt with them.
Look it up.
but
only one cop I like, he's technically Kansas City. And he's the only one in the entire town I don't like, everyone else is.
They target me because of my skin color. They're like, look at this pasty ass cracker. Yeah. Like, yeah, fuck that guy. Maroon like that. Yeah. Yeah, I still raise his insurance premiums.
You're white as a saltine cracker, dude.
Mine and my sister's did. It was really bad because I went 50 on Vine one
I
day.
ended up paying
And
$2
the state trooper was right behind me. And I like looked at my
I
ear and I go,
accidentally paid
fuck, I'm gonna get
for
pulled
something
over.
I didn't
We just
want,
went right
which
past
was
me.
like
I was
in the
Yeah,
house with.
yeah. I tried doing the thing, like, officer, I
So
wasn't
we used to
doing
be in the
nothing.
Mini Cooper, like, it didn't even
So-
get to, it was like barely pushing, okay, go get me, I was like,
Right
why?
after I'm drink.
Yeah, it was going
And
100.
Well, they always
because I
treat me so
smelled those
stupid.
down because I
That happens.
needed it.
They're like,
Well,
they
I'll
try to
let
get
you
me
get back
incriminate
to it.
Thanks,
myself.
because I kind of like the pasty
No, I
white
pulled you over.
comment
I'm
over
like,
there.
I don't
He's talking
know
about
shit.
cops.
Tell me.
I am part of the.
Did we tell him that your dad's a
That's
cop?
what you want from me.
I know I did something illegal, but I'm
My
not gonna
brother's a
give you
sheriff.
another reason to give me another ticket.
He's a
So,
I
douchebag.
always just like, I don't know why you pulled me in front.
His stepfather works
I'm gonna
for.
rapidly reach for the
cops.
glove box. You ready?
Is it like an actual
My
sheriff
insurance.
or is this shadow deputy?
Here's my insurance,
He's a
here's
sheriff.
proof of ownership.
Not here though. Lions.
I had a cop follow me all the way from the roads to 41st and Hall. That 4-way stop. Oh, that's bullshit, man.
You can't follow.
Maybe they were going the same way.
They can't
All
follow
the way
you
from
more
the
than
road.
2 blocks.
Well, like there was one time I was going down a Vine and I didn't know my headlight was out. The cop turned on 13th and pulled me over on 5th.
That's bullshit.
And I was like,
They can't follow
and
you
he's
for
seen
more
my
than 2
uniform
blocks
in
or
my
it's
backseat. He's
stalking.
like, do you work for the hospital? I go, yeah. And my sister was on the phone and she was working, so she heard that I got pulled over. And I was like, yeah. And he was like, well, do you know why I pulled you over? Nope. Your headlight's out. Okay, thanks.
I got pulled over with my roommate one time, and he's like, when you ask who you're coming from, tell him your mom's house. I'm like, yeah, I don't want to get shot, but that's really funny. If I had steel balls, I'd totally do it, but I don't, so. So where are you coming from tonight? Why don't you ask your mom?
Can't you get a ticket for that?
Probably.
You
Actually,
disrespect-
no, the Supreme Court just ruled you can flip cops off now. It's freedom of speech.
Hell
They
yeah.
used to give you tickets, and you can be like, here's my license, here's my insurance. How are you today? Yeah, good, cool. Yeah, it's cool.
I ever just wanted to like go up to a table full of cops and holster one of their guns and put it on the table.
I'm an alpha male now, bitch. No, you don't do that. That's how you definitely get shot.
Yeah.
Well, it's good to know you haven't lost all sense of, you
Hopefully
know.
you edit this video before you.
Oh,
put it
no.
out there.
You just gotta put it up. Yep.
That's funny.
Nope, put the whole way up. Maybe you'll get a chuckle when you're trying to review.
Oh yeah, my students will really get a chuckle when they're in high school and looking at the video.
Oh,
And you've cussed all the way through it.
Just put up some
Okay.
bloopers, like here's the actual thing, here's the bloopers.
Mom,
Don't
this
watch
guy's
if you're
brilliant.
under
Like cops.
18.
All right, so let's discuss 5.1 and 5.2. We already looked at 5.1. Checkpoint. 5.2, they're talking about graphing the exponential function there. Hold on, this is not our book. That's why I can't find what I'm looking for. Pretty sure that I picked the right one here.
Well, let's investigate the graphs of exponential functions like this. We'll start with this basic function and then make some changes and see how that changes the graph. Y is 2 to the x power. If I use a point plotting method, then I would build a table of values like this and I would plot a few points. Do notice though that as I'm building the table, if I go into the negative values, like for -2, you see if x is -2, then I put a -2 in place of this x. And that means that I have a misplaced base. So I end up with a fraction. I end up with 1 over 2 squared, or 1/4. That's how I arrived at this 1/4 situation here. Another interesting situation for this family of exponential functions is what happens when x takes on the value 0. See, since x is in the exponent, when x itself is 0, we have 2 to the 0 power, which is 1. All right, so that's going to be kind of a prevailing point in all of our exponential functions that are in this little, or that are configured in this way. Okay, plotting the points, constructing the graph, I get this graph, and let's talk about some characteristics that we see. We see a domain. The acceptable replacements for x would be all real numbers. We can see that graphically here, perhaps more clearly than we can from our function. The range would be positive values only. Notice that the graph lies entirely above the x-axis. Also, we may be noticing that the x-axis is an asymptote for this graph. That is, the graph is getting infinitely close to the x-axis as we go out in this direction. Notice also that this is a continuous function, and it is continually increasing throughout its domain. That is, this graph is continually increasing. Others may not, but we'll see that as we go. All right, now let's change the base of the exponent. Let's consider g of x to be 4 to the x power and see what happens to the graph. We'll think of this as y is 4 to the x power. We build a table of values. Let's plot these points. 0 goes to 1. Same point as we had before. Again, that's a prevailing idea in this family of functions, that the point 0, 1 is going to be on the graph of the basic functions. All right, then 1 goes to 4. 2 goes to 16. Now 2 is off the graph. So that graph is coming down like this, rather sharply. And it kind of makes a turn right here. Then -1 goes to 1/4, and -2 goes to 1/16. So it's getting really close to that x-axis very quickly here. You see, so it has this kind of behavior. Now, from this, we're noticing that if this is the graph of 2 to the x, and this is the graph of 4 to the x, it seems to be the case that as the base of the exponent in exponential functions gets bigger and bigger, the graph rises more sharply and more sharply. And that is the case. And on the other hand, as this base gets smaller and smaller and sort of approaches 1, then the graph has a tendency to sort of lay down. For example, if I were constructing the graph of y equals 1.2 to the x power, then that graph might look something like this. See, it'll be a gently rising graph. So roughly 1.2 to the x power. All right, now let's consider what happens if we change things a little bit within the exponent. 2 to the negative x. 2 to the negative x. If I build a table of values, it would look like this. If x is 0, see, once again, we have 2 to the 0 or 1. That familiar point is still on the graph. If x is 1, though, we have -1 as the exponent on 2. Misplaced base, this becomes 1/2. If x is 2, we have -2. Misplaced base, 1 over 2 squared, 1/4. If x is -1 minus -1, that's 1. So 2 to the 1 power is 2, and so on. These are vaguely familiar coordinates here. Let's plot those points. 0 goes to 1. Then 1 goes to 1/2. 2 goes to 1/4. -1 goes to 2. -2 goes to 4. -3 goes to 8. And the graph looks like this. You may notice that this is a reflection of our first graph. That is, here is our first graph, and if we reflect it in the y-axis, then it imprints right here. So this is 2 to the negative x power.
So transformations, if you look there on 269, there are transformations, and we've kind of dealt with these transformations before. What happens to the graph if I add x plus 1 instead of just the exponent x? You see there it rises more sharply with the x plus 1. If I do 3 raised to the x power minus 2, you see that I drop 2 there. 3 to the x power and negative 3 to the x power, you see it's a reflection. And the one you just did, 3 raised to the negative x and 3 to the x power is a reflection as well. Just knowing graph behavior there. If we're talking about compounded interest, that is something that is exponential. Initially, the interest that is put onto that is small, and then it continues to grow faster and faster. And we'll watch a couple of those videos here in a little bit. Maybe not today. Go over to page 274 for me, please. On 274, when we're talking about logarithms, that is an exponential speedy way to increase numbers as well. When you look at A on example 1, it says log 2x, where x is 32. I'm looking at 2 being my base. So I have a 2 base. I don't know what that number is. Essentially, I'm looking for my exponent there. Okay? So 2 raised to the what power gives me 32?
Which one are you looking at?
Number 1, A.
A.
So 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. So 1, 2, 3, 4, 5. So 5 is my answer there. So the number after the log becomes your base number or your big number.
So B would be 0.
Yeah.
And then,
Because 3 to the 0 power gives you 1.
and then
4 or C,
B is negative.
4. What number gives me a 2?
Negative half.
Just positive half.
Positive half.
Yeah, because if it's a negative, then it's going to replace the base.
So you said that B was 0?
B is 0, yep. Because I have 3. So what place gives me an answer of 1? 3 to the 0 power. Anything with the 0 power on it is always 1.
And then D is negative 2.
Yeah. So 10 to what exponent gives me 1 over 100? Okay, so I've got to have 2 to get the 100, and then negative to get the 100 underneath on the bottom.
What does it mean when there's like a number before the log?
That's a good question.
hope it's simple, but I doubt it.
For that one?
Yeah, that would be easy in math.
Oh my gosh. Mister, I have an A plus, nothing's easy in
I
math.
have an A minus, I don't know how.
I have an 8, I don't know what I have of an
I am completely dumbfounded.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
This is a tutorial on how to use logarithms with a calculator.
Okay, so you can look that up. Talk about properties of logarithms. Properties of logarithms actually is over in section 3 on page 282.
First of all, the product property. This is the one that's related to the idea that when you multiply like bases, you add exponents. And it's this. The logarithm of a product is equal to the log of one factor plus the log of the other factor. Doesn't seem to be any relation whatsoever to the related exponential form. But remember, we're dealing in the world of exponents. And in the world of exponents, when you have a common base and you're multiplying, you add the exponents. That's an exponent, this is an exponent. That's kind of the basic idea. Now, you're not going to remember it like that. You're going to remember it like this, that when you're taking the logarithm of a product, you can rewrite that as the log of one factor plus the log of the other factor. And we need to also be able to go the other way. There are circumstances where we need to expand and other circumstances where we need to sort of contract this expression. So when we have the sum of two logarithms and the bases are the same, then we can write this as the logarithm of a product, the log of a product of 5 and x. And notice I'm not writing a logarithmic base here, and I'm doing that because I don't want to add confusion to the situation. But this property works for all bases. It can work for ln, for example. It could work for log base 7, log base 5, whatever, as long as the base is the same in all of these expressions. Okay, the quotient property. The quotient property works like this, that when we are dividing and we have like bases, we subtract exponents. Okay, when we take the logarithm of a quotient, it is the difference of logarithms. It is the log of the numerator minus the log of the denominator. And for the power property, the one we're raising power to power, we multiply exponents. Well, it's the idea that we have the log of x to the 5th power. We can write 5 as the coefficient of log x. This is 5 log x.
So all that is
And
your
we can go the other way.
exponent.
That is, we have 5 log x. This is the log of x to the 5th power. So this is just a two-way street here. Same idea with this. If we have the difference of two logarithms in the same base, then we have the logarithm of a quotient, and it's the quotient of this rascal over that. Okay, now, I would love to give an easy proof for these and a nice, good relationship for us to remember this, but there isn't one. I'm going to show you how this comes about, and I'm going to relate this back to the exponential form. But it's not the kind of proof that you would tend to remember very much. But let me show it to you. Let's take this expression and just put it up here. All right, now just follow this little discussion. Suppose we just let log 5 and log x have a relationship to a variable or to a letter. I'm going to let A stand for log 5 and B stand for log x. Now that allows us to change each of these to an exponential form. That's the purpose of doing this. So this is equivalent to, or implies, let's see, now I'm using
God bless
the
you.
common log base of 10. If I used 7, it would work out the same way or whatever, but I'm just using log 5. No base is indicated, so it's understood to be 10. So we have base exponent equals 5. So 10 to the a power is equal to 5. And here, if b is equal to log x, then 10 to the b power is equal to x. All right, now, let's go through and make some substitutions. We have log 5x means, well, what's 5 and what's x? Well, over here, 5 is 10 to the a power and x is 10 to the b power. Okay, so if 5 is 10 to the a and x is 10 to the b, then we have this. But we know that when we multiply in like bases, we add exponents. So we have 10 to the a plus b. And the log of 10 to the a plus b, we know from before, from the last section, that if the logarithmic base and that number are the same, then we simply have a plus b. But what is a plus b? You see, we simply have that exponent, a plus b. But what are a plus b? Well, a and b are log 5 and log x. So a is log 5, b is log x. And so log 5x is log 5 plus log x. Now, once again, I'll mention that this kind of looks like smoke and mirrors right now. And that confusion, if there is any, is expected at this point. But with a little experience, it'll all become clear.
Okay.
Natural logs. That's ln, right?
Yep.
Oh, well, look at that. Okay. Great.
And you do have an ln on your calculator as well.
We know that log x, if no logarithmic base is written, then it means log base 10 of x. All right, we know that. But on the calculator, ln x, there's an ln button on the calculator, and that means the natural log of x, which means the log of base e, the log base e of x. Okay, so log base e of x means the same thing as ln x. Now, all of our rules, all of our little things that we went over here involving logarithms, regular logarithms with bases other than e, apply to natural logarithms. So we have, let's see, ln1 means log base e of 1. Remember what that was? We're looking for the exponent on e that will give 1. Well, that exponent needs to be 0. And here, ln e, well, that just means that we have log base e of e. You see, and when the logarithmic base is the same as that number, the number here is 1. And again, ln e to the fourth is simply 4 because we discovered that this is log base e, you see, of e to the fourth power. And this is a request for the exponent on understood e that will give e to the fourth. What exponent needs to be applied to that e? Well, a 4 does, you see. So we just read it off like that. Now, once again, since this is a logarithmic base that is found in the calculator, we can just punch the calculator to make the calculations for natural logarithms. If we want ln 7. Now, what we're calculating here for is the exponent on e that will give 7. That is, e to what exponent gives 7? And that exponent turns out to be 1.95. And we find it by pressing ln and then 7 and then enter, and we get approximately 1.95. Now, this is a very long decimal. It's an irrational number, so I've rounded it to this value. And also ln 25 turns out to be 3.22. You might try this on your calculator just to get a little practice with it. But remember, what this means is we're looking for the exponent on e that will give 25. That is, e to what power is 25? Well, e to that exponent will give 25. And actually, it's e to approximately that power because it's a rounded number.
Okay, and over on example 8, 278, you do have a few for the calculator that you could work. It shows you exactly what to push into your calculator to get it to work properly.
What page is that on?
278.
See, I don't see that ln number online. In his item.
Capital, look for capital L, capital N.
Yeah, that's what it is. Looks like an N, yeah.
You see, suppose we try to take the log of -4 in, let's say, base 5. The base really doesn't make any difference here. But it's the idea that we set this equal to x, and then we have, in exponential form, 5 to the x power is equal to -4. And so we're looking for an exponent to apply to 5 that will give a result that's negative. You see, now, although x can take on both positive and negative values, it's never going to cause this expression to become negative. So this is an impossibility. We just simply can't take the log of a negative number. Now, since we can't take the logarithm of a negative number, that leads to some restrictions on the domain of logarithmic functions. Now, we said that basically log functions, log x, you see, log base 10 of x, log base 2 of x, those kinds of things have a domain which is easy to establish from the reflection of exponential functions. All right, but let's do it from a different perspective here. Let's think, well, okay, we can't take the logarithm of anything with positive values. So to establish the domain here, we'd like to know the values of x that will cause x plus 3 to be greater than 0. You see, and subtracting 3 on both sides, we find x to be greater than -3. So x is greater than -3. And we could kind of see this if we construct a graph of this, and we could do that with transformations. You know, we could take that basic graph of the log function and then shift it over to the left 3 and see that we have x values on that graph that are greater than -3. That's another way to look at it. But I kind of like this algebraic approach as well. Consider this one. Now notice that this is a natural log function, and all of the aspects of log functions for any base apply to natural log functions, because after all, this is just a logarithm in base e. So it's really not any big deal. The shape of the graph is pretty much the same as the shape of the others. And domain and range, same idea here. Okay, let's talk about domain. The domain is found by kind of saying to yourself, well, we can only take the logarithm of positive values, so we'd like to know the value of x that will cause 2x minus 3 to be greater than 0. So we add 3 on both sides, divide by 2, whoops, not equal, greater than. So x is greater than 3 over 2. X is greater than 1.5 then as the domain of that function. Now, what about this one? Now, this one is kind of interesting from a graphical standpoint as well as from an establishing of the domain standpoint. Now, if we're finding the domain, we want the values of x that will cause this value to be positive because we can only take the log of positive values. So, we want to know what value of x will cause 3 minus x to be greater than 0. If I subtract 3 on both sides, I get this. And then if I multiply on both sides by -1, I'll clear the negatives. But I also need to change the sense of the inequality because I'm multiplying in an inequality by a negative number. So this is x is less than 3. X is less than 3. All right, now what that tells us about the graph basically is this, that if we don't know anything else about the situation, we know this much, that at 3, for x values less than 3, the graph is going to lie over here, and the asymptote is going to be here, you see, for x values to be less than 3. So we're over here with our graph. Now, how does that graph behave? Does it do this? Does it do that? How does it behave? Well, that's another matter for consideration. Now, we might try to go through the process of thinking about transformations using the information here, but this is pretty tricky. This is a very tricky situation to deal with transformations. Tell you what, let's look at it on the graphing calculator.
Now
Here's
let,
our function, and the graph has the expected kind of behavior. Now, to verify the calculated domain of x being less than 3, we can sort of see it from looking at the calculator display here. Here's a tick mark at 1, and then 2, and here's 3. And it appears that the graph makes its appearance on the coordinate plane for x values less than 3. Well, to verify that further using the trace button, we can trace over and get near 3.
all right, now we're going to watch just on decay, which was the last thing that we needed to do today. And so you can see the exponential factors of it.
Let's talk about the decay model a little bit. It turns out that in figuring out the age of organic matter, a lot of times carbon-14 is used. Carbon-14 is an isotope of carbon, and it's a very stable isotope. And it has a rather definite half-life. And a half-life means the time over which half of it dissipates. And that half-life is very long for carbon-14. It turns out to be 5,570 years is the half-life of carbon-14. And now, the exponential decay is of some kind of organic material is modeled by this equation. All right, so we're given the equation here. Notice the appearance of 5570 right here, and the base of the exponent is 1/2. And we won't talk about how this was derived or anything like that. It doesn't make too much difference in our calculation here. It's a little bit beyond what we want to do. Here's what we want to do. A bone that originally contained 100 milligrams of carbon-14 now has 70 milligrams of carbon-14. What is the approximate age of the bone? You see, when the bone first came into existence, it had 100 milligrams of this carbon-14. Now it has 70. So we're talking about these two values. This is the initial value, initial quantity, and the quantity now. You see, initial quantity, 100 milligrams. The quantity now, 70 milligrams. So that's what we pop in here, and then we solve for T. Here's how it goes. So the initial quantity, 100 milligrams. The quantity now of carbon-14 is 70 milligrams. We just pop those in, and now we want to solve for T. So we go about the business of doing that using the structure that we've talked about a number of times before. Divide on both sides by 100, and we find this to be 0.7. And then 1/2 can be thought of as 0.5. And away we go with jumping into the exponential world by using logarithms, and I'm applying common log on both sides of the equation. Now the exponent becomes a coefficient here of log 0.5. And now we want to solve for T, so we need to eliminate the 5570, and we need to eliminate log 0.5. To eliminate 5570, since it's in the denominator, we'll multiply on both sides by 5570. So 5570 will become a coefficient of log 0.7 over here. And at the same time, I'm dividing on both sides by this amount, by log 0.5. So I divide over here by log 0.5, and now this is just a calculator push. So we find the time to be approximately 2,866 years for the age of that bone.
Easy, right?
I didn't catch how many.
Did he have to use logarithms?
2,866 years. Did you have to what?
Did he have to use logarithms?
Yes, because it will even, for a while it won't age at all, and then all of a sudden, bam, it's aging quite fast. Exponentially.
So you couldn't have got that without using the logarithm?
No. At least I don't think so. All right, so brief introduction. I don't want to go too far into logarithms. I want to kind of introduce it. Next week we will talk more about properties, about changing bases, more about logarithms. And then you will be done. I am going in here to look for @WebAssign here real quick. I don't want this one though because it will not work. Let me go here.
I think this one's due the 14th. Yeah, this one's due the 14th, and the other one's due The 28.
Okay, that's right.
Is that what you're looking at?
Yep.
That's supposed to do in 2 weeks. And we have chapter 6 and 7.
Yeah, 6 and 7 go together. Chapter 6 is,
Only 50 problems or 49. Okay.
chapter 6 is,
It's 57. Chapter,
systems of equations and inequalities, and chapter 7 is Kramer's rule, and so it goes together.
matrices.
Yep.
Oh my God.
Okay, so there is your information. You should be able to go in and at least kind of peruse your assignment.
What happens if you look at your taxes filed by April 14th,
April 15th,
April 15th?
they will fine you.
Because I'm pretty sure I don't owe any money. I shouldn't have paid an extra last year. I've made them set extra money aside, so I wouldn't have to pay it.
How much did you make? What are your W-2s say?
Oh, I don't know, I didn't make more than like 15,000.
Okay, but if you made more than 12, you've got to file.
Yeah, I'm going to wait on one more tax form in the freaking mail, but they won't send it. Yeah.
They have to send it.
It's for non-taxable. They just, I keep calling them trying to get, oh, we'll get one on its way. and-
It's for non-taxable income.
Yeah. For a structure settlement, I got one right, dude. And, but they sent me the letter saying it's not taxable, but they send me a W-2 I can put in anyways. And they won't send it to me. I got all my old jobs with W-2s, I got them all put in on TurboTax. I'd have to only use that because I should be able to use W-2.
What about your educational expenses and stuff?
Oh, yeah, the business too, I think.
Okay.
Think.
Any computer or anything you needed this year? Or last year?
Yeah.
Calculator, anything? You've got to add that in.
Oh,
Do not forget to add that in.
I'll do that.
That's educational expenses. Thank you, Margaret. Have a good night. You too, dear. Okay. Yeah? Is your work done? Okay, this
I work with my kids this week, but Monday nights I just stay here, so I have to drive home if you want to come right after the meeting.
So don't forget to put that in because that'll give you an extra 25% of whatever that computer costs.
Really?
Yeah, educational expenses give you 25% of it.
Wow, that's nice.
Yeah.
When I was doing my TurboTax, I essentially like